this lecture will be enough of field theory to begin the theory we're interested in, and anything else can be developed later on. So we might also need a lecture on polynomial ring, just to like review some important definitions and properties and concepts. And other than that, we'll be starting in the core of the course in a few videos. So as a continuation on the study of field theory, there are a few things that I want to remind you of this lecture. So first of all, I remind you, so let's say you have a ring R with the addition and the multiplication, and I remind you a ring is it's a set which, when we equip it with two binary operations, we get that R with the addition is a group, and we get that it's an abelian group, to be precise, and we get that R with the multiplication is a monoid, and this monoid is not necessarily commutative, and when it is when the operation multiplication is commutative, we call the ring commutative ring. And we also require that the addition and the multiplication are distributive. So if we wanted to summarize what a ring is, this is what we might say. So if you feel that some background in ring theory is missing, I advise you to refer to my course on abstract algebra, where I cover group theory and ring theory. So I also remind you that if we have two rings, we have what's so-called a ring homomorphism between these two. So let's say we have a ring R and a ring S, right? So the reason I'm introducing here homomorphisms is that you will see in field theory that most of the time we're not only interested in fields, but we're also interested in maps between fields. We're interested in automorphisms, for example, and we will see how important is that as we go in the lectures. So we do need a concept of what a homomorphism is. So I remind you that if we have two rings or an S, right? A map phi from R to S is a ring homomorphism. If it preserves the addition, multiplication, and the multiplicative identity. So to state this in symbols, what we mean is that we require that phi of A plus B to be phi of A plus phi of B, phi of AB to be phi of A, phi of B. So here we have the multiplication, and phi of 1 of R is equal to the 1 of S. So just a couple of things here. This addition is addition in R, right? So this is a plus of R. So we're adding elements in R. So this is happening for every A, B in R, right? This addition is addition in S. So these are elements of S. When we map an element here to here, they become elements of S, and we're using the addition of the ring S, right? This multiplication is the multiplication in R, and similarly, this multiplication is the multiplication in S, right? And this is the multiplicative identity of R, and this is the multiplicative identity of S. All right, so the other thing I want to mention is that the reason we are not requiring phi of 0R to be equal to 0S, like we're not requiring phi of 0 to be 0, like phi of 0R to be phi of 0S, because this follows immediately from this thing over here. So to see this, just here, like a side note, to see this, you notice that phi of 0R is equal to phi of 0R plus 0R, right? So we have this, which is equal to, by property number 1, so this is we have three properties of ring hom. This is going to be phi of 0r plus phi of 0r. So this is some basic property of ring homomorphisms, and then you add the inverses both sides and you get that this is 0s, right? So these are just easy properties for you to recall. Here's a definition for you, right? So let f and f prime be fields, right? And like I remind you what fields are, just rings, plus we require that f with the multiplication, if we take away 0 from it, we require that this is an abelian group, meaning we require that multiplication is commutative, and we require that every element has an inverse. Every element has a multiplicative inverse. So this definition we went over last time. You can refer to my previous video to see more details. So a map phi from f to f prime is a field homomorphism if first of all we require it to respect the addition, just as for ring homomorphism. Phi of a plus b equals to phi of a plus phi of b. Second, we require it to respect the multiplication. And it's important here to note that and just for us to avoid the trivial case of the zero map, we're gonna define phi of 1f to be 1f prime. Alright, so it's literally a ring homomorphism, but I wanted to keep this definition for you because we're gonna need it. So the first lemma we're gonna prove, let phi from f to f prime be a map of fields such that it respects addition. In other words, it's a homomorphism over addition, and it also respects multiplication as such for every a, b in f. Then one of these two cases happen. It's either that phi is the zero map, or phi is an injective homomorphism. It's an injective ring homomorphism. So let us prove this. So let us start the proof over here. So phi of 1, this can be rewritten as phi of 1 dot 1. So this is the 1 of f, right? So this is equal to, by the multiplicative property, this is equal to phi of 1 times phi of 1. If we rearrange terms and we use the additive inverse, we have phi of 1 times 1 minus phi of 1 is equal to 0, and the 0 is the 0 of who? This is the 0 of f prime, right? So we have this case, right? So here comes the importance of the word field over here. Here comes the importance of taking a map of fields, right? So if phi of 1 is not 0, then it has an inverse. Phi of 1 inverse exists, right, in f prime. Then if we multiply by this inverse both sides, what we get is 1 minus phi of 1 is equal to 0 f prime. Maybe this wasn't, there's an extra step that is not needed, but just to mention here, this means that phi of 1 is 1. So it's if we assume that this is not 0, if we assume that it's not the 0 map, it must be that phi of 1 is 1. So this is the first thing that we have, and we in addition have that the map phi is injective, and this is an important property that, as we shall see later, since we'll be interested in automorphisms of fields, we will see later that um, like if you have a map phi from f to from f to itself, right, you automatically have that this if you have it a ring homomorphism, then you automatically know that this map is injective, right? You automatically know that, and to prove that it's an automorphism, it would suffice to prove that it's surjective. So this is a kind of important property to keep in mind. If you have a ring homomorphism of fields and it's not trivial, it's automatically injective, and this is a very good property to keep in mind. So let us prove why it's injective. So we're also under this assumption, right? We're assuming that phi of 1 is not 0, which means that phi of 1 will force it to be 1. All right, so let us see why phi is injective. So this is an important property to keep in mind, as I mentioned. So let us see why it's injective real quick. Well, since phi is a ring homomorphism, it suffices to prove that the kernel of phi is 0, right? This is what suffices to prove. And to prove that the kernel of phi is 0, it suffices to prove that phi of r is 0 if and only if r is 0. Now this direction is trivial because this is by definition of ring homomorphism, just as I showed you. If you have a ring homomorphism, then phi of r is automatically 0, phi of 0 is automatically 0. So let us prove this direction, right? So we want to prove that phi of r is 0 implies that r is 0. So what we will prove is the counter positive of that. We will prove that if r is not 0, then phi of r is not 0. So this is what we'll prove. And why is this true? Well, if r is not 0, then r inverse exists in f, thus phi of 1 is equal to phi of r dot r inverse, which is equal to phi of r dot phi of r inverse, right? Which is equal to so this is equal to 1, and thus you just have you have on the right hand side you have 1, and you know that 1 is not 0, and on the other side you have a product of two elements, so it can't be that phi of r is 0, because otherwise it would be the case that the right hand side is 0. Thus this implies that phi of r is not 0. And this completes the proof actually of why it's injective. So this is the first property to keep in mind. Here's how you remember it. Non-trivial field homomorphism is injective, is always injective. This is very important to keep in mind. Okay, so the next concept I want to review is what's so-called a characteristic of a field. So what is a characteristic of a field, right? So this concept also exists for rings, but we're pretty much interested in it for fields now. So a characteristic of a field is the smallest integer which when you multiply 1 by you get a 0. Okay, so before I just restate this definition more formally, let me just give you a simple example. So let's consider the field fp, and I remind you fp is the field z mod pz, right? So this is the field of, if we take p to be prime, this is gonna be the field of all numbers that are reduced residues modulo p, and we're defining addition. I remind you a plus b is defined to be a plus b mod p, and a dot b is equal to a dot b mod p. All right, so this field has a characteristic p, I claim. So let us see why. Well, if you take any element in this field, let's take any a, right? If you multiply it by p, right? What happens if you multiply that element by p? You have p times a, but we know that multiplication, the way it works is that we always reduce the element that we have mod p, but anything that multiplies p mod p is going to be 0 mod p, right? So particularly if we multiply 1, we will get 0. If we multiply p by 1, we will get 0. Now, why is it the smallest integer? Why is it the smallest such number? Because if let's say n is strictly less than p, and and um and notice that it can't be the case if n is strictly less than p, and it's between like strictly positive and strictly less than p. It can't be the case that n dot 1 is 0, because these are the elements that are strictly less than p, and these are the ones that are positive, right? So if you multiply any of these by 1 and you take mod p, like you don't get 0, right? Because these elements are strictly less than p, so they are actually the reduced mod residues mod p, and they don't reduce to 0. So this is never 0, and this is why p is the smallest positive integer, where p dot 1 is 0, which means that the characteristic of fp is p, right? This is a very important thing to keep in mind. Okay, so let me just give you a definition real quick now that we've motivated it. So given a field f, the characteristic of a field f, denoted as char of f, is the smallest, I stress here, it's not any random number, it's not any random number that does that. It's the smallest such number. It's the smallest positive integer such that n dot 1 is 0. Now, it might be the case that such an n doesn't exist. Like, there are some fields where such an n does not exist, in which case we call the field of characteristic 0, right? So if such an n does not exist, we call the field of characteristic 0, right? Let me just give you a quick example here. We're gonna be seeing these, I guess, but let's give you this example here. So we showed that q in the previous lecture. We showed that q with the usual addition and multiplication forms a field, And if I ask you now, what's the characteristic of q? What's the smallest number? We want a number n. We want the smallest such number, but that satisfies the property that when we multiply this by the 1 of q, we get 0. Well, there is no such number, right? Because multiplication in q is defined in the usual sense, like this is the real number 1. So n dot 1 is just n here, right? So if n dot 1 is 0, then n is 0, right? So but n was assumed to be strictly positive, then there is no such n, right? So this is a contradiction. So in other words, the characteristic of q does not exist, or some people usually call that, as we mentioned, the characteristic of q is 0 in this case. Alright, so because it doesn't exist. Alright, so the next important lemma that we need from field theory is that a field can only have a characteristic 0 or a prime number. Like, this is surprising enough, but it might seem not very useful at the moment, but it's actually very useful, as we will see later. So let us prove this lemma. Let us prove this. Suppose f is a field. So we have a field f, and let n be the characteristic of f, just to simplify notation, right? Then n dot 1 of f is equal to 0 of f. So this is what we have so far. Now suppose that n is not a prime. Okay, so suppose n is not a prime, and let's also suppose and not 0, right? So we're supposing that n, which I remind you, this is supposed to be a positive integer, or 0 if the characteristic of the field does not exist, right? So this is bigger than or equal to 0. So if n is not a prime and not 0, then it's a composite number. Then n is a composite number. Namely, n can be written as a product of a dot b, where a and b are strictly bigger than 1, right? So this is what we have. And thus, what we have from here is that we have n dot, so we have n dot f, n dot 1 is 0, right? So this is what we have, which is equal to ab dot 1f, right? Ab dot 1f is just because this is an integer, right? We know that we have distributivity, so we can actually rewrite this as a dot 1f times b dot 1f. And once we've done that, we notice something here. We look at the right hand side, and we see that we have a dot 1 dot b dot 1 is equal to 0. But in a field, this cannot happen. Why? Because since a is not 0, a and b are not 0, then a dot 1f and b dot 1f are not 0. They're not equal to the 0 of f. And in that case, since they're not 0, then they have inverses. And if we, for example, multiply by the inverse of this thing, if we multiply by the inverse of this thing both sides, we see that this will imply that b dot 1f is 0, but we already have that it's not 0, thus it's a contradiction. So it can't be the case that this inequality holds, which means that this equality holds, which means it's a contradiction, right? This whole thing leads to a contradiction. So this is actually a contradiction. And what does this contradict? Well, it contradicts the assumption that it's not a prime and not a 0. So it must be one of these. It must be either 0 or a prime, as we mentioned. Probably there's an important concept that I should cover because I've been using something about fields that I don't expect the audience to know, though it's an elementary thing. Let me just do a definition here. Given a ring, R, a zero divisor of R is an element A of R such that there exists B in R such that A dot B is equal to 0, and A is not 0 itself. And also B is not 0. If there are two elements A and B, both of which are not 0, and they multiply to 0, then we call A and B zero divisors. Let me just give you a quick example here. So if you look at the ring Z mod, let's say 6Z, right? So this ring is the ring of all integers reduced modulo, like the reduced residues modulo 6. So these are 0, 1, 2, 3, 4, 5, and that's it. And we're taking addition and multiplication modulo 6. If you take the number 2 and you multiply it by 3, this number and this number, these are not 0 in this ring. Like these are not 0 here. However, if we multiply these, this is the same as 2.3 mod 6, which is equal to 6 mod 6, which is equal to 0, right? So these are two non-zero elements of z mod z is 6, but they multiply out to 0, which means that these are 0 divisors, right? So this is the definition of what a zero divisor is. And the property that I was using about fields that I wanted you to know is that so this is a note here. A field has no zero divisors. And let me prove this because this is important. Just one line proof. So let me just give this field a name, F, right? A field F has no zero divisors. So in a field, there can't be zero divisors. And I'm gonna show you, here's where I used it, right? Since A.F, A.1F, and B.1F are not zero, it can't be the case that their multiplication is zero, because in a field there is no zero divisor. Because if this equality were to hold, that this on the right is equal to 0, then it would mean that A.1F and B.1F are zero divisors, but these are elements of the field, and the field doesn't have a zero divisor. And this what clarifies the contradiction. This is another way to clarify the contradiction. So let me just tell you what the proof of this is. So a field F has no zero divisors, and here's the proof. Suppose there exists A and B that are both non-zero in F, and suppose that A dot B is equal to 0, meaning suppose that F has zero divisors. This is what we're supposing. If F has zero divisors, then it must be that there are two elements that are non-zero and they multiply out to 0. But since A is not 0, A inverse exists, and thus if I multiply by A inverse both sides here, I get that B is 0. But this is a contradiction, because I already assumed that B and A are not 0. So this is a proof by contradiction. This completes the proof. So please keep this in mind. A field does not have zero divisors. So far, the definitions covered were like just general definitions that you would see in an abstract algebra course. But these, from now on, will be kind of building the tools or the terminology used in Galois theory. So we start by the definition of what a field extension is. So a field extension. So most of the time in Galois theory, what we'll be doing is that we're interested in understanding some field F, right? And the way we're gonna understand F is by building up to F. Like we're gonna consider subfields of F, K1, K2, and so on. We're gonna be considering subfields of F, and we're gonna building our knowledge until we reach some useful info about F. So in this case, the field F is called a field extension. A field extension of these things, of this field, right? So let me just give you the definition in a clearer term. So a field F is an extension of a field. A field E is an extension of a field F if F is just a subfield of E, meaning F is a subfield of E, right? And the usual notation for this is that you write E and you write a line like that, and you write F, just to present the hierarchy, because later on we'll be having like a field, and it has like it's an extension of many fields, and we're gonna be plotting diagrams and something like that. So this is a notation. Another notation for the field extension is E over F, right? So a field E is called an extension of a field F if F is a subfield of E. As simple as that, right? So there are some important things here to keep in mind whenever you see this definition. Um, um, I should make here two clear notes before I define to you what a degree is. So here are some notes. Um, if E slash F, I'll start using the notation to get you used to it, is a field extension. If that's the case, if F is a subfield of E, then first of all we have the characteristic of F is equal to the characteristic of E, and second we have that E is a vector space over F. So let me clarify what I mean here. Let me justify here why this is true, why it's the case that the characteristic of F is equal to the characteristic of E. Well, the characteristic of F, it's the smallest integer n such that is equal to 0. So this is the characteristic of F, right? So it's the smallest smallest positive integer such as this happen. But wait a sec, if F is a subfield of E, then 1F is equal to 1E. Thus the characteristic of F is equal to the characteristic of E. This is trivial, right? Because I mean the same n is the n that works. It's the same n is the smallest integer that makes 1E equal to 0. Alright, so and the other thing I want to clarify here is that E forms a vector space over F, and I remind you a vector space is a set which, when we equip it with addition and scalar multiplication, it satisfies some axioms, but mainly the most important ones of these are like these two operations are binary. We require these to be binary. We require V to be closed under these operations, and we require that that inverses exist, and we require some other axioms. So if you look at E as a vector space over F, so here we usually have a reference, right? When we talk about a real vector space, we're considering scalar multiplication by elements of R, right? So a vector space, a real vector space, is one where we're defining scalar multiplication. So this is defined for all R in the real numbers, right? So this is a real vector space. Now, what is an F vector space? If F is a field, right? If F is a field, an F vector space, let's call it V, right, with addition and scalar multiplication, is a vector space where the scalar multiplication, where this is defined is defined for multiplication of elements of vectors of V by elements of F. So let me clarify here. For example, when we talk about complex vector space, in that case we're defining scalar multiplication by complex numbers, which means we're gonna define what it means to take a complex number c and multiply it by a vector v. So this is a complex number, as opposed to a real vector space where we require c to be real. Now, in an F vector space, C has to be in F, or C can be in F. This is how we're defining it. So when we say E is an F vector space, what we mean is that we're defining, so E is a field, we know E is a field, so we're defining the scalar multiplication by elements of F. And what does it take for a vector space, or for a set to be a vector space, when we define scalar multiplication by some elements of a field? Well, it takes it to, well, we need the scalar multiplication to be a binary operation. But multiplying elements of E by elements of F is okay, because first of all, multiplication is defined in the field, because in a field, addition and multiplication is defined. So the multiplication between elements of F and elements of E are defined because F is a subfield of E. Because F is a subfield of E, then we can multiply elements of F and remain in E, right? We can multiply elements of F by elements of E and remain in E. This is very important, right? So, since we have a binary operation by scalar multiplication, you can check the other axioms. I'm going to leave it for you as an exercise, that E does in fact form an F vector space when we view the scalar multiplication, when we view the multiplication of an element of F by an element of E, when we view it as scalar multiplication in the vector space. Alright, so these are the things I wanted to clarify before I make the new definition, which is the definition of degree of a field extension. So given a field extension E over F, so E and F are fields and F is a subfield of E, then we define the degree of E over F, we define the degree of the extension, and we denote it as such. We define it to be the dimension. So E over F is the dimension of the vector space E, but over what field? Over F, right? So E is a vector space over F, and we're defining the degree of this extension to be the dimension of E over F. I'm going to give you an example, but before we go over this example, which is a bit of a harder example, let's go over a simpler example. Okay, we know, at least from the previous video, that the real numbers and the complex numbers are fields. This thing we know. But also, we know that the real numbers is a subfield of the complex numbers. So this also we know. And thus, C over R is a field extension. Alright. So the question of what is the degree of C over F is a legitimate question. So what is the degree? I wanna make you used to this notation. This is called the degree of C over R. So what does that mean? Well, if you consider C as a vector space over R, what is the dimension of that vector space? But it might be hard for you to imagine directly what I mean here. So let me just clarify for you. So what is C? Well, C is the set of all numbers of the form A plus IB such that A and B are real numbers. So this is what we have. And what we're asking here is that what's the dimension of So first of all, we're asking. First of all, we're considering C as a vector space over R, and what does that mean? It means that we're considering, well, C. We know what the addition is for C, and we're gonna define a scalar multiplication by elements of R, because we want to consider C as an R vector space to be. We take a real number R. And what we do is that we multiply an element A plus IB in the usual sense. We multiply it RA plus IRB, right? So this is how we're defining scalar multiplication. And when we do this, we get a vector space C over R. And the question is, what's the dimension of C over R? What's the dimension of the vector space C over R? Well, what's the easiest way to get a dimension of a vector space? Well, the easiest way is to find the basis and find the cardinality of the basis, right? So what is the basis of C over R? So if you look closely here, you see that there are two elements that are being involved here, namely 1 and I. Right? So what we're doing is that we're taking linear combinations of 1 and I, and we're getting a basis for C, because every element in C can be written as A dot 1 plus I dot B, if you wish. So every element of C can be written in this form. Thus, this is a basis for C over R, for the vector space C over R. So this is a basis for it, right? So since this is a basis for it and it's of length 2, then this is the dimension is 2, and thus the degree of this is 2. So let us just take another example to refine your knowledge of what a field extension and its degree is. So here's the proposition that we're trying to show. Q square root of D is a two-dimensional vector space over Q. But what's important here, I remind you that Q square root of D, if we take D to be not a perfect square, namely D is not equal to n squared, in order not to get the trivial case as we discussed in the previous video. So this is the set of all numbers of the form A plus B times square root of D, where A and B ranges over Q, right? So this is like, if we take B equal to 0, right, and we run A over Q, we get all of Q, which means that this contains Q. And thus Q square root of D over Q is a field extension. And when we say that the dimension of Q square root of D over Q is 2, what we really have is that the degree of the field extension, Q square root of dq, is equal to 2. So let us prove this. It's important. It's also trivial to see it if you look closely at the definition of what Q square root of D is, right? Every element, let me just write it here. Every element of Q square root of D can be written as a linear combination A dot 1 plus B dot the square root of D, right? Thus since 1 and square root of D are linearly independent, I'm gonna justify what I mean here. Since these two elements are linearly independent, then 1 square root of D is a basis for Q square root of D over Q. and thus the dimension of q square root of d over q is 2, because this is the size of the basis to that vector space. And what do we mean here when we say these are linearly independent? Remember, when you studied linear algebra, like linear dependence meant that like let's say you have two vectors v1 and v2, right? These two vectors were said to be linearly independent if you take r1 v1 plus r2 v2 equals 0. This should imply that r1 equals r2 equals 0. This is the definition of what linear dependence is. But who were R and R1 and R2? Who were these, right? So in R, or let me just say over R, linear independence was defined as, so just before I do this definition, this completes the proof here, right? If I tell you why these two are linearly independent, this completes the proof that I wanted to mention. I recall, over R, linear independence was defined as, so if you take two vectors v1 and v2 are linearly independent if you have a linear relation between these, then it must be a trivial linear relation. So if r1 r2 are real numbers and we have this, then r1 equals r2 equals 0. So the only relation that we have is the trivial relation. So over a general field F, so this is a definition for you. Over a general field F, two vectors, like over a general field F and a vector space E over F, two vectors v1, v2 in E, because this is the vector space, are linearly independent if and only if we have the relation r1 v1 plus r2 v2 is equal to 0, where r1 and r2 are now in F. So this is the distinction here, right? This is the distinction that I'm trying to make. So it's a similar definition, but now we're working over F, thus the scalars are in F. Like, there is no meaning, if we were working over F, there is no meaning to 2v1. Like, let's say F is not a field of real numbers, right? There is no meaning to 2 times v1, because the scalar should come from the field over which you're defining your vector space, right? So the scalar here, this is a scalar multiplication. Remember, these are vectors and these are scalars. So this is scalar multiplication. So the scalar should come from the field over which your vector space is defined. So if you have this linear relation where the scalars are in your field F, then it must be that R1 equals R2 is 0. And as an example, let us prove why 1 and square root of d are linearly independent over Q. Why over Q? Because the vector space we're talking about is Q square root of d, and we're taking it over Q, right? So it suffices here to prove that these are linearly independent over Q. So let us see why these are linearly independent over Q. Well, suppose, and I want you here to pay attention to what I'm saying. Suppose R1 and R2, the scalars should come from the vector space, from the field over which your vector space is defined. So these should be in the field. and suppose that r1 times 1 plus r2 times square root of d is equal to 0. If that's the case, then if we rearrange terms, we get that the square root of d. Now, since we're working over the rational numbers, these are numbers, so we can rearrange things. So there are two cases here. If r2 is 0, then r1 is 0, and we're done. Because if this is 0, then r1 is 0, and we're done, because this is what we want to prove. We want to prove that they're linearly independent. Now, if r2 is not 0, then we can rewrite these terms. We can rewrite this equation as minus r1 over r2. We can write square root of d as minus r1 over r2, but this is a contradiction. Why is it a contradiction? Because this is an irrational number, because we assume that d is not a perfect square, and this is a rational number. If you divide two rational numbers, you still get a rational number, but this cannot be true, and thus this is a contradiction, and it must be the case that r2 is 0, which means r1 equals r2 equals 0.